Good afternoon, everybody, and welcome to the 38th webinar in the RUS Copernicus webinar series. My name is Teresa Roth, and I will be guiding you through this session today. And we will be looking at sea ice monitoring using Sentinel-1 data and machine learning. First, let's have a look at the outline of today's session. And as usual, we will start with introduction to the RUS service, and then I will shortly discuss sea ice monitoring using Earth observation, and the production and standards for ice charts. Then we will move on to an introduction to the Sentinel-1 satellite, followed by study area and data used for this exercise. And finally, we will log into the virtual machine for the demonstration part, and we will conclude the session by 30 minutes of Q&A session where I will answer all your questions. Now, if you have any questions during the demonstration or presentation, please don't hesitate to send us your question using the questions tab in the GoToWebinar panel as soon as possible, and me and my colleagues will take care to answer your questions right away so as not to have a pileup of questions for the Q&A session. Now, if the question is interesting for the entire audience, I may leave it for the Q&A session to address it for everybody to take advantage of it. Anyway, if any questions are missed, they will be included in the Q&A summary document that will be published together with the webinar recording. And of course, as usual, the webinar is being recorded and it will be available soon on YouTube and on the rus-training.eu portal, together with already said Q&A document. Today, the session is going to be a little bit longer, about 2 hours, and let's now start with the introduction to the RUS service. Now, as you may already know, the RUS service stands for Research and User Support for Sentinel Core Products, and it is a project funded by the European Commission and managed by the European Space Agency. Its main objective is to increase the uptake of Sentinel data via the provision of free and open scalable platform, which is implemented on a powerful computing environment in the form of virtual machines, which are pre-installed with open source toolboxes, such as, for example, Snap, QGIS, BRUT, or development environments for R, Python, and many others. Last but not least, we also offer a specialized remote sensing help desk, which is there to answer any questions that you may have about which data to choose, about specific applications of Sentinel data, and so on. And then we also offer dedicated training activities, such as, for example, this webinar. Now, since September last year, there have been some changes introduced into the RUS 2.0 version, and we will still provide the services in two categories, which are the training activities and the category of individual users and R&D projects, but there is some changes into the provision of virtual machines. So first, for the training activities, we will provide training in three categories as before, which is face-to-face, webinars, and support to external training organization and operation. And now let me go through each in turn. Each face-to-face event, or these days a virtual classroom, will cater for about 20 participants, with each participant provided with a virtual machine to repeat the exercise in real time with the trainer. The type of the virtual machine will depend on the specific training needs, and the VMs will be available for a minimum of 1 week, with the possibility of extension to up to 1 month. Of course, the ICT and EO support will be available to the participants for the entire duration of their virtual machine. Then we have the monthly webinars, such as, for example, this one, and the recordings and the PDF guides, including also the Q&A summary document, will be available to everyone on the RUS Copernicus portal and the RUS training portal, and a limited number of VMs will be also available for webinar replay. For the externally organized trainings, maximum of 30 virtual machines will be available per event, and the participants will benefit from the support from the ICT team. Now moving on to the individual users and R&D projects. Unfortunately, the RUS version 2.0 will no longer provide virtual machines to this category of users, but RUS Copernicus will continue to provide support to individual projects and R&D through a new solution with Docker container image, which contains the complete RUS virtual environment and the tools, and it will be provided upon request. The container can then be deployed on users' own infrastructure, which can be cloud-based, either in-house or acquired from a commercial provider, such as, for example, one of the DSs, or it can also be deployed on a personal or work laptop or PC. And the ICT team will, of course, be available to guide the users through the deployment procedure. Now, finally, as you probably already know, RUS is implemented in two portals. We have the RUS Copernicus portal, where you can find all the information about the initiative, about the availability of virtual machines, and you can also register and request a virtual machine or the Docker container image. Then we also have the RUS-training.eu portal, where you have registered for this webinar as well. And you can find here all the information about our past and future trainings. And for all the webinars, you can also find here the recordings and the Q&A summary documents. Moreover, you can also check our e-learning portal and any news about our training activities. Now, as I mentioned also in the beginning, any recordings of our webinars are also available on YouTube on our dedicated RUS Copernicus training channel, and you can find them there in a few days after the event. Now, that is all for the introduction to the RUS service. If you have any additional questions, please don't hesitate to let us know. And let's now move on to the introduction to the topic. Now, sea ice is frozen seawater, and it is a major component of Earth's climate system. It effectively controls heat, moisture, and chemical fluxes between the ocean and the atmosphere, and it dramatically alters the surface albedo and redistributes salt and fresh water in the ocean. It provides habitat for a wide range of organisms, from microbes to whales, that are specifically adapted to its presence and seasonal patterns. There is clear evidence, as you can see on the graph on the right, that the sea ice extent is decreasing as a result of climatic change. If we look at the Arctic, studies report a decrease in sea ice extent by 12.2% per decade, while annual mean sea ice thickness has decreased by more than 2 meters for the central Arctic basin between 1975 and 2012. With the decreasing sea ice extent, lower albedo and water circulation create a positive feedback loop, which further contributes to climate change. Accurate ice information is crucial to understand and monitor these changes in the Arctic environment and also their effects on the global climate change. On the other side, the decline in ice extent is creating possibilities for new sea routes and the exploration of natural resources in the Arctic. The Arctic region is estimated to have 22% of the world's oil and natural gas reserves, and a large portion of the natural resources in the Arctic are offshore and unexplored. As a result, more industrial activities are expected in the region in the future, and supporting information for safe navigation will be necessary. Sea ice is a very complicated medium that morphs as it grows and ages, and it contains brine pockets, air bubbles, and other impurities that leach out with time, especially if the ice survives a melt season. And this has led to the distinction between the seasonal or first-year ice and perennial or multi-year ice, with the latter being fresher and harder and much greater hazard for ships and structures. Now, on the image to the right, as I've mentioned, you can see the Arctic sea ice extent, with the red dashed line showing the minimum ever recorded, which occurred in 2012. But you can also see in yellow the first years on record in the National Snow and Ice Data Center that are significantly higher than already the median of the period between 1981 and 2010. Then you can also see the start of this year, so 2021, and we are already moving even below the record minimum of 2012. Furthermore, in blue, you can see the average of years between 2011 and 2019. And here you can see that this average is much closer to the record minimum of 2012 than it actually is to the median of the preceding 30 years. Now we mentioned why sea ice is important. However, how do we monitor it? Sea ice data from satellites represent one of the longest Earth observation records from space. The variations in temperature, emissivity, and reflectivity of sea ice and the differences compared to the surrounding open ocean make it an ideal application for remote sensing. Now we can name a few of the most important variables derived from remote sensing. First, ice concentration. Since the 1970s, microwave radiometers have monitored sea ice daily, and they are the backbone of sea ice monitoring, especially sea ice concentration, on a large scale for climatic studies and ice extent monitoring. Then we have the ice thickness, which is generally considered as one of the most important sea ice variables for both operational purposes and modeling. Sea ice thickness is needed to compute the total ice volume, quantify the heat fluxes between ocean and atmosphere, as well as to plan any operations in the sea ice. Usually, laser and radar altimeter data from missions such as ISAT-2 or CRYOSAT-2, and previously from sensors on board of ERS and ENVISAT have been used to retrieve large-scale thickness. The next variable is ice type. Now, classifying sea ice into different types or stages of development related to thickness can provide a proxy not only for thickness, but also for other important ice attributes such as salinity, roughness, and strength, and possibly also snow thickness on top of the ice. In particular, the separation of the first-year ice and the multi-year ice is important for navigation. I have mentioned this already before, as well as for monitoring the impacts of climate change. Active microwave scatterometers, SAR sensors, and passive microwave radiometer sensors have been used to differentiate the ice types, but each carries its own limitations. Now, the next variable is the ice drift. Ice drift datasets are used in climate models for validation and to estimate sea ice flux and improve sea ice modeling. Microwave radiometers and scatterometers and SAR data are used generally to monitor ice drift at different scales. Finally, in our list, we have albedo, which is a critical variable for the realistic modeling of seasonal evolution of snow and ice thickness and is generally derived from optical data. This is by no means an exhaustive list, and of course, you can find many more variables referenced in literature. Now, as I've mentioned already with the thickness, on the right, you can see a beautiful animation showing how combining data from ESA's CRYOSAT satellite, which measures thick ice, and ESA's SMOS satellite, which measures thin ice, allows for the measurement of thickness for both first-year and multi-year ice, and so it allows for the calculation of sea ice volume for the whole Northern Hemisphere. Now, when we look at SAR data, the interaction of SAR with sea ice is a complex phenomenon that depends on radar parameters such as frequency, polarization, or the incidence angle, but also on the ice characteristics such as salinity, roughness, thickness, density, orientation, or inclusions and impurities, and also on the properties of the overlying snow cover. And those can be, for example, moisture content, grain size, density, or the thickness of the layer. While SAR data constitute one of the most used sources for sea ice monitoring, it is very much reliant on human experts for classification. However, a growing number of studies are developing models for automated classification of sea ice types and other variables from SAR. Now, the cross-polarization channel is known to be more sensitive to the difference in scattering from sea ice and open water than the copolarization channel. However, for operational purposes, the combination of both HH and HV polarizations have been successfully used for the ice edge detection and ice type classification. Automated classification is also made difficult by the fact that the sea ice backscatter is not independent of incidence angle, and the relationship further differs between the different sea ice types and characteristics. Moreover, if we look specifically at Sentinel-1 sensor, the cross-polarization images suffer from strong noise, which is usually negligible for land applications, but causes strong contamination over the ocean waters, which have very low backscatter to begin with. The accuracy of any automated classification will benefit from the use of advanced thermal and textural noise removal algorithms. And for example, here on the right, you can see images that have been corrected with one such algorithm, which was developed by Park et al. In 2018 and 19, and removes the thermal and textural noise from the copolarization channel. Now let's look at ice charts specifically. Ice charts are depicting the distribution of sea ice and icebergs and are produced on operational basis by a number of national and international services. The services producing ice charts in the EU include, for example, the Copernicus Marine Service, or CMEMS, the Norwegian Ice Service, or the Danish Meteorological Institute. There is, of course, many others that I have not named. These charts are used by a host of parties, including policymakers, regulators, climate scientists, hydrologists, flood prevention agencies, or emergency incident responders, but maybe most importantly by ship and offshore platform operators. The overall purpose is, of course, to provide a general awareness of ice distribution and to enhance the safety of marine navigation and offshore operations, and to increase public safety, minimize property damage, and aid ecosystem management. The ice charts are mainly produced by experienced human operators, manually analyzing SAR and other imagery for ice concentration, type, flow size, and occasionally also identifying leads, ridges, and rubble fields. It is time-consuming and labor-intensive process, and it is subject to the varying skills of the individuals. Over the last years and decades, the objective of the majority of research for ice charting is directed at finding methods to analyze SAR and other data to produce ice charts automatically with high accuracy. In our exercise, we will use the ice charts provided by the US National Ice Center for the simple expedience of being provided in the Esri shapefile format, which is very easy to work with. They are based on a combination of different imagery and are produced primarily using SAR data, microwave radiometer data, scatterometer data, and visible and infrared imagery from a variety of sources. In addition to imagery, other data sources are used, such as, for example, drifting buoy data, ice model predictions, limited ship reports, meteorological and oceanographic observations, and ice information provided by other national and international centers. The daily charts that they provide include only two ice concentration categories, and these are 1 to 8 tenths and 8 to 10 tenths, meaning therefore 10 to 80% and 8 to 100% ice concentrations. The weekly charts, which we will use to train our model, contain much more detailed information and separate ice areas to include total ice concentration, ice types with their respective concentrations, and ice forms where applicable. Now, when you see an ice chart, they will follow the guidelines and standards as defined by the SIGGRID 3 format. The SIGGRID, or Sea Ice Grid, was originally proposed in 1981 as a way of digitizing sea ice charts to aid climatological analysis and improve operational ice chart production. The ice characteristics, as defined by a number of code tables, were described at specific grid points. SIGGRID was adopted by the World Meteorological Organization in 1989 as the international standard for ice chart data in digital form. With the advances in GIS technology and the adoption of GIS by ice services for chart production, it became much easier to describe ice chart information in vector format rather than at grid points. The vector format has a number of advantages, such as, for example, it preserves all of the information in the original chart, and the chart can be reproduced, reprojected, or rescaled without loss of information. And in the table on the right, you can see the different ice codes that are currently in use in the SIGGRID 3 vector archive format for sea ice charts that has been in use since 2010. Now, in this table, you can see the codes that are used in the weekly primary stage of development chart, which is provided by the US National Ice Center and which we will be using to train our model. In the screenshot or in the image on the right side, you can also see a little subset of the ice chart provided in image form. Now in the chart, you can see 6 major classes. The first one is new ice, which is the ice that began to grow few hours or days ago and is between 0 to 10 centimeters in thickness. Then we have young ice, depicted here in purple, which is the transition between the new and first year ice, and it's approximately 10 to 30 centimeters thick. Then we have the first year ice, which is no more than one winter's growth and is between 30 to 200 centimeters. And in the ice chart here, we have it divided into further three categories, which is the thin first year ice up to 70 centimeters, medium first year ice up to 120 centimeters in thickness, and thick first year ice, which is more than 120 centimeters thick. Now, each of these categories have their own specific code. And finally, we have also the old ice or multi-year ice, which is the ice that have survived at least one summer's melt. Most of the topographic features in this ice are smoother than on the first year ice, and in general, it is thicker than 2 meters. Then you also have these white polygons, which include the areas where glacier ice or icebergs are seen. Now let's move on to the introduction to the Sentinel-1 satellite. The Sentinels are a family of satellites built by the European Space Agency, or ESA, for the needs of the EU Copernicus program. Copernicus is to date the largest Earth observation program in the world, and all its satellite data are available under free and open policy anywhere in the world for any application. The Sentinel-1 satellite constellation is formed by two identical satellites, Sentinel-1A and Sentinel-1B, which are placed in the same orbit faced 180 degrees apart. The constellation allows a repeat frequency of 6 days over Europe, the Mediterranean, northern coast of Africa, and parts of the Antarctic. The satellite acquires data in 4 modes, which are the strip map mode, the interferometric wide swath mode, the extra wide swath mode, and the wave mode. Now, the primary modes are the interferometric wide swath mode with VV plus VH polarization over land, and the wave mode with VV polarization over open ocean. The extra wide swath mode, which we will use today, is primarily used for wide area coastal monitoring, including ship traffic, oil spill, and sea ice monitoring, usually with HH and HV polarization. The strip map mode is only used for small islands and on request for extraordinary events, such as, for example, emergency management. The spatial resolution, of course, differs by mode and also by the level of the product. The data are generally available at 3 different levels, which are the single look complex, the ground range detected, and the level 2 data. In this exercise, we will use the extra wide swath mode, which offers 400 kilometers swath width, and the products are available either in full or medium resolution. The medium resolution, which we will use, corresponds to approximately 93 by 87 meters, with a pixel spacing of 40 by 40 meters. Now, the methodology that I will show you today is by no means developed by me and is completely based on a methodology proposed by Park et al. In their paper called Classification of Sea Types in Sentinel-1 Synthetic Aperture Radar Images. In previous research, they also developed the mentioned Sentinel-1 denoising algorithm, which applies thermal and textural and angular correction to the cross-polarization channel of Sentinel-1. Now, they have achieved very high accuracies for most ice types, especially for the separation of open water and ice. We cannot replicate the scale of the study, of course, in our little exercise today, and we will only use 28 images for the training, and we will apply the methodology over small area. For this reason, please don't expect our results today to be quite as good as the ones reported in this study. Now, for this exercise, we need a number of different data sources. I have already mentioned Sentinel-1 data, which you can download from the Copernicus Open Access Hub. But apart from that, of course, we will need ice charts, which can be downloaded from the US National Ice Center, and I will show you in the virtual machine a bit later. We might also need the Copernicus orbit vector files. It may be that for your Snap version, you will not need those. However, a few months ago, the website that has been used by the Snap software to retrieve the orbit vector files has changed. But for some versions of Snap, this change has not yet been reflected, and therefore the automatic download of the orbits will fail. This is the case for the version that I'm using today, and therefore I had to go and download the orbits manually and place them into the designated Snap folder for the software to be able to find them. Similarly, we might need the calibration auxiliary data. These are used by the Sentinel-1 denoise algorithm that I have already mentioned. And again, these have been stored in the same repository as I've mentioned before, that is no longer functioning. And for this reason, we might need to download them manually and place them again into the appropriate folder for the software to be able to find them. Alternatively, you can also change the code specifically to include this new web page. Now you can see on the right my chosen study area. It's very small. It's in the Strait of Denmark between Greenland and Iceland. It's depicted in yellow. And if I search in the Copernicus Open Access Hub for all the images covering this area between my chosen period, which is 11th of October 2020 to 22nd of March 2021, you can see that I receive 422 GRDM products. Now, if I wanted to process all of these, it would be very time demanding, and in the scope of this exercise, we don't really have time for that. However, I chose to use only a single orbit, and here you can see. So like this, we have 29 images, from which 28 we will use for the training and 1 for the final classification. And let's now look at the software used for our exercise. So we will be running our exercise in Python using Jupyter Notebooks, and the processing will require quite a lot of different packages, including already the ones that I have mentioned, such as the Python bindings for Snap, called Snappy, or for example, the Sentinel-1 denoise algorithm, which is also available as a Python package. And to manage our environment, we will be using Anaconda. Anaconda is an open source distribution for Python and R, which includes quite a number of handy tools for package management and so on. Moreover, it allows our environment to be reproducible, meaning that I can give you a simple file which details all the packages, and Anaconda can create the environment for you in order to be able to run this exercise on your virtual machine or on your computer. And if you are not familiar with Jupyter or Anaconda, I would advise you to follow an excellent training given by my colleague Miguel. You can find the link here, and you can find also the recording on our YouTube channel. It's called Processing Sentinel-1 Data Using Snappy. And there, everything is explained specifically about Anaconda, using Snappy within Python, Jupyter Notebooks, and so on. During this exercise, we will not go too much into that, although I will show you how to set up the specific environment I need. And now, finally, let's proceed to the virtual machine for the actual demonstration. And here we go. Now, when you receive a virtual machine in RUS, if you're familiar with it already, you will know this. It is accessible via your browser, simply with a link and login details. So now let me log in to my virtual machine. And here we go, it will open. I will increase the size of the window to be a full screen. And here we are. Now, when you see the screen like this, it is more or less similar to any screen or any desktop of a laptop or a PC that you're familiar with. It is based on a Linux Ubuntu 16.04, so it is not Microsoft, as most of us, me included, would be used to. However, generally the navigation is very similar to any type of laptop that you can have. Now, to start the exercise, first we will have a look at the training folder, which is saved and shared. Training, and it is this one, CRYO04 sea ice classification. And then you open it, you find 3 folders here, and there's the aux data folder, which is, you could say, the most important one. It contains the Jupyter notebook that we will be using for the processing. It also contains the environment description file, which is here, which we will use to build the environment that we will be using for the processing. And then it also contains a pre-made graph that we will be using, and it contains a text file which specifies how to create and run the environment. Now, I'll go back to this a little bit later, We also have here the folder that contains the ice charts, which have been reprojected and clipped to our specific study area. And then we have here, these are just folder with images that are then shown in the Jupyter Notebook. You'll see that in a second. And we also have here a shapefile folder, which is including some shapefiles that we will be using during the processing and some visualization styles as well for QGIS. And we will then move on to the original folder where all the data that we want to process are saved. Now you can see that I have 30 items here. Okay, one of them is TXT, so 29 items as I have shown you before in the presentation. They are all coming from the same orbit, and they are acquired from the 11th of October 2020 to the 22nd of March 2021. Now you can see that I have the files already downloaded. If you don't have them, of course, you can download them by simply going to the browser. And if you're working on the RUS virtual machine, it will right away open in the Open Access Hub. If you're not, you can simply go to the path of the Sci-Hub or the Copernicus Open Access Hub, and then you can go to the Open Hub here to download your data. Now, to download the data from the Copernicus Open Access Hub, you need to have an account. I will not go into searching and downloading the data from here, since we are addressing this topic at every single webinar in the past. So you can, for example, check the webinar of my colleague Miguel I have already mentioned in the presentation, because there he goes into detail on how to search for Sentinel-1 data and how to download them from the Copernicus Open Access Hub. Now let's go back to the folder here, and let's go to the processing folder. Now you can see that in my processing folder, it's already populated with pre-processed data. And this is due to the fact that the pre-processing of the data of single image takes about an hour and a half. And of course, that is a lot of time that we do not have during this webinar. So I have the data pre-processed. I will show you how to process them anyway. And it would be all automated. If they were not processed, the script would automatically process them. So here they are already pre-processed. And we can now start with the setting up of the environment. So let me go back to the aux data folder. And as I've mentioned here, we have the environment description file. And we also have this TXT file, which details the steps that we need to take in order to create the environment that our Jupyter Notebook is going to run in. Now, I have mentioned that for the management of our environment, we will be using the Anaconda, and we will be using Anaconda Python distribution as well. So the entire environment is created with Anaconda, and Anaconda will take care of installing all our packages, and it will use to do this file, the YML file. And if we open it, you can see that this file simply details the name of the environment, and it details all the packages that are installed. Now, I know that this is a lot of packages, but bear in mind that each of the packages, such as NumPy, has its own dependencies, so it installs additional packages in order to be able to run. And basically, it contains also the location where this environment is going to be saved and all the packages that should be installed. So let me close this file now, and let's open the setup environment TXT. As I've mentioned, here are the exact steps, just simply written, and the commands that you need to create this environment. Now, unfortunately, this YML file is not the only thing that we will need to install. So in normal cases, if we only use Python packages, you can just use this file and you can simply create the environment and go right away. Now, if you're using Snappy and the other software that I have mentioned, which is the Sentinel-1 denoised, these are not possible to be installed using this description, and therefore they are not included in this YML file. This means that we have to install them additionally. So these are the steps that are basically detailed here. But as you can see, there is not so many commands, so let's start with that. Now in my aux data folder, I'll just simply right-click and I go to Open Terminal here. which will open a new terminal window, which has the root path here to the aux data folder. Here you can see in the beginning of the path, this is the environment that is currently being used. At the moment it's base, but of course later we will want the environment that we will now create to be the active environment. So to start, we will simply copy this command. Which states or passes to Conda the command to create an environment based on this environment description file. And here we go, we are finished. And now we have to activate this environment. So that's what I've mentioned before with the base environment being activated here. And now we want to activate the newly created environment. And the command is simply conda activate and the name of the environment. Here we go. And now you can see that in the beginning of the path, now I have the name of my new environment instead of the base. Now the next step is to install Snappy. Snappy is the Python bindings to Snap, and we will be using it today for several different steps. So let's now go to the Snap installation folder. Again, I can just simply copy the command. Here we go. And now you can see that the path has changed to the path that I have specified here, so to the installation folder of Snap. And the next line will basically create the installation files for the specific version of Python installed within my new environment. So let's do that. And this is going to take, again, a few seconds. And here we go. Now this command sometimes appears not to be complete. However, once we get this message here, we can simply click on Ctrl+C, which will stop the process, but the process actually has finished. So now we can go to the next line, which will change the directory again, and it will change it now to the .snap Python snappy directory, where the installation files have been created. And finally, we can run the Python setup py install, which will install Snappy bindings into our new environment. And here we go. And now Snappy is installed, and we can proceed with installing the Sentinel-1 denoised tool. I will test both installations a little bit later when they're both done. And now let's install the Sentinel-1 denoised. Now, to install the Sentinel-1 denoised, you first have to download it. So you have to go again to the browser. And I have the path saved here in favorites. So here it is. I will also provide the path for you, of course, in the Q&A summary document later. And here we have the software in GitHub, and we can simply download it as an archive. I will not do this anymore since I have downloaded previously, but you could just click and it will be downloaded. And then you can go, if you're in the RUS machine, it will be downloaded in the home RUS, otherwise, of course, into your downloads folder. And you can see that it has already been downloaded here for me. So now I would simply extract it, and I would get this folder here. There we go. And you can see that in this folder, there's this setup.py file, which serves to install this software into the specific environment. So let's now go back to my terminal, and I can simply just change again the folder or the path to this directory, so this unzipped directory. Here we go. And I can simply then just run the setup py that is located in this directory to install the Sentinel-1 denoise to my CRYO04 environment. And here we go. So now both of the softwares are installed. Now let's test them. So I will just type Python. Here we go. And I will just import them. So first I will import the snappy. Here we go. And we get the correct response. Perfect. Snappy has been correctly installed. It has been imported to Python successfully. And now let's test also the Sentinel-1 denoise. And we can test it by importing this command. And again, no errors. The modules are recognized and we have it installed. Perfect. Now we can simply just restart the terminal. Since we are here anyway in Python and we want to be out of Python again, we can just type exit and brackets to get out. But we can also just simply close the window and go back to our AUX data folder and reopen it again. Now, when we do that, we are also back in our AUX data folder, and we can simply activate our environment again. So let's copy the command here. Now, we must not forget this step, otherwise we will not be able to run the Jupyter Notebook. So let's click paste. There we go. And we now have the environment activated, and we can launch the Jupyter Notebook. Here we go. The Jupyter Notebook opens in the browser, and you can see that it opened in the directory that I have as my active directory from which I have opened the Jupyter Notebooks here. And you can see it has one notebook located in this directory, and that's the CRYO04 sea ice classification version 4 that we will be using today. Let me just open it, and here we go. Now, you remember I was mentioning this folder with the images. So this is basically just the images that are included within the notebook. And it just, they have to be located in a specific location so the script knows where to find them. Now, as I've mentioned already before, this notebook and this exercise will not actually require you to do any coding. However, if you understand Python, it will make following this exercise much easier for you. Now, I am not a Python expert per se. So of course, if you are Python experts, you may find that my code in some ways is maybe not as effective as yours would be or not as elegant. I apologize for that in advance. However, it seems to work and it works for me. So let's continue. Now, in the beginning, I just include some information about this tutorial. This is mostly the information that I have already given you during the presentation, but still it may be useful if you're using this tutorial sometime in the future. And of course, there are some links on information about Sentinel-1, as well as links to the Python tutorial and to Jupyter Notebook documentation and Jupyter Notebook tutorial, where you can learn more about Jupyter Notebook and how to run it and what are the commands and so on. Now, the exercise is divided into following sections. We will first start with loading the Python modules. So those are these modules that we have installed when we were setting up the environment. Then we will move on to defining some user functions. These are functions that will be then used multiple times in the text, and we just don't simply want to repeat the same code over and over again. So we just create a simple function that will perform this piece of code for us as many times as we need it. Then we move on to the only part which requires user input. This, for example, contains paths to the original data, to output folders, and additional attributes or parameters that we wish to define. Then we will load and visualize the input data. So these will be the Sentinel-1 images that I have shown you in the original folder. And then we will move on to the preprocessing of this data using, here I have written only snappy, but actually it's using Sentinel-1 denoising algorithm, snappy, and also GPT. I will explain why I use both GPT and snappy in that step. Snappy and GPT are both basically referencing the same software. It's both Snap. Snappy is simply the Python bindings for Snap, and GPT is the terminal version of Snap. And I will explain why I use both of them when we get to that step. And then we will move on to extracting the training data and training and validation data from the preprocessed Sentinel-1 imagery, as well as from the downloaded ICE charts. And that brings me to the fact that I have not actually told you yet how to download the ICE charts. I will explain that once I go through these steps. And then we will move on to the classification using the random forest. So first we have to train the model on our training data. And finally, we will classify the last image in our time series. And we will perform also some post-classification filtering to enhance the result a little bit. And finally, we will visualize the result. Now, I've mentioned that I forgot the ICE charts. So let me just go back to the folder first. So you know that I have mentioned that the ICE charts are saved here in the auxiliary data folder. Here we have them. And these are the original ICE charts. They are downloaded as zipped folders. Each of those contains a shapefile. Shapefile format generally consists of 4 different files. So that's why we have so many more files here. And these have been already pre-processed very quickly in QGIS. And basically the only processing that has been applied to them is to reproject them into the same projection as our final pre-processed Sentinel-1 images will be, and also clipping them or subsetting them to a smaller study area, because these charts contain the data for the entire Arctic. Now, to show you how these data look, I've already done so in the presentation, but we can go to the website from which I have downloaded them. And this is the US National Ice Center. So let's go here. And here in the products tab, you can find the Arctic. And here we go. Now you can download these charts as a PNG. So these are always the latest charts here, but you can also download the archive data, and those can be downloaded in a variety of different formats. So as an image or as a zipped shapefile. So if I go here to the data files, I can then have several options. And again, I have the daily charts, and I have the weekly data, which contain both the more detailed concentration and also the stage of development and so on. And I can also have KMZ files for the daily and some others. Now, the most important for me, of course, are here the weekly Arctic shapefiles. And I can simply here go to Archive. And here I can choose the specific period for which I wish to download the data. So again, it would be 2020, October, and let's say 5 of October, for example, and then March and 22nd of March. So these data are usually corresponding to images that have been acquired sometimes between 3-4 days before the publication of the chart. It can be a little bit less as well, in the last 3 days before the publication, basically. So they may not be exactly the situation as it is on the date of the publication, of course, because sea ice is a dynamic medium. It moves all the time, so it might not be exactly the same as the day of the acquisition. So when we search like this, I can just click search, and here I have all the ice charts for that corresponding period. Again, I can download all of them. I would unzip all of them, and then I would simply process them in QGIS with those 2 steps that I have mentioned. I will not go into that here. If you're interested to know how I've done that, please let me know and I will explain it during the Q&A session. And now finally, we have all our necessary data downloaded. We have the ice charts, we have all the auxiliary data, and we have the original data, and we can proceed with running the code. So in Jupyter Notebook, to run a cell, you simply click Ctrl plus Enter, and the cell will be run. So now we can test if all of our modules are correctly installed and the environment is correctly set. So let's click Ctrl Enter. And here we go. We did not get any error. So you can see that while the cell is running, you have here the star symbol, which indicates that the cell is currently running. You also would see here this circle as full. Now, when you see a number, that means this code cell has been run. You can see that the cell after does not yet have any number here. And let's move on to the next step, which will be the user-defined functions. Now, to facilitate the processing of the data and avoid the duplications of different parts of code in the exercise, which is anyway quite a long exercise already, I have created some functions here in order not to have to repeat the same piece of code over and over and over again. Now, the first one simply adds quotation marks. This is a little tiny function that we use to avoid errors when we are passing commands and paths to the terminal through the subprocess command, in case the paths contain spaces. Then we have the execute command, which simply calls a terminal and executes a command and prints the output beneath the cell. And finally, we have some functions that deal with geospatial data. We have the points to array, which simply takes an array or a raster array that has a specific size and resolution and burns points from Esri shapefile into this array. So let's say we have an original Sentinel-1 image that has been pre-processed, and now we want to have the exact pixels that correspond to these point coordinates that we provide as a shapefile burned into another layer, which will be just binary layer, including zeros on the pixels where the points are not, and ones on the pixels that correspond to the point locations. Now, this is specifically for the transformation of the sampling points when we create the training data. And finally, since we have the ice charts, and the ice charts are shapefile, to simplify the processing of these and to match them again with the Sentinel-1 preprocessed data, we will rasterize specific attributes in these charts to have the same exact dimensions and resolution and create an array of exact same size as the input raster data or as the Sentinel-1 data converted into an array, in order to basically have multiple layers that fit perfectly on one another, and each value corresponds to the exactly same pixel. Now for this, we need the data source, so the JDAL raster object, which will be used as a model. Then we need a polygon shapefile, which is the ice charts, and we need also the name of one of the attributes in the shapefile that we wish to use to populate the raster values. So this is the attribute that we wish to rasterize. Now here, by default, it is set to total concentration. So you remember when I was showing you the table of the different variables that are included in the SIGRID format. There was CT, for example, stands for total concentration, and then we have the SA, which stands for stage of development and corresponds to the stage of development of the thickest ice. So these are our user-defined functions. Again, I can simply load them to memory by pressing Ctrl-Enter and running the cell. Here we go. And now we move on to the user input data. Now, this is the only part that would require some editing. For example, here we have to provide the input directory. So in our case, this, of course, is the original directory where all the Sentinel-1 images are downloaded into. Then it would be the preprocessing data directory, which in our case is just called processing, where all the preprocessed data will be saved. And then we have mask, Now this shapefile, so this is a shapefile and it corresponds to a land mask that we will use to mask our data in order to avoid classifying and polluting our values with the land pixels that we are not really interested with. This shapefile you can find in the aux data folder, in the shapefiles folder, and it's right here. And basically it just contains for our study area polygons covering Iceland and Greenland, so any landmass. Then we also have the graph file, which contains the snap graph for preprocessing the data. I will show you the graph when we get to the preprocessing, and I will also show you how to create it and how to save it, so you can provide the path here. And then we have the points file, which simply contains the sampling points that we will use to create the training data or sample our data to create the training data set. And again, these points have been randomly generated over a specific study area. There is about 1,000 points. And these will be basically values for these points will be extracted from every single image and ice chart to create the training and validation data set. And finally, we have also the location of the preprocessed ice charts. Now, we also have here some additional parameters. These are parameters that will be later passed into the graph file here, and they are the border pixels. Now, this is number of border pixels to discard from each image in order to remove any border noise. It is used in a subset operator. Then we have the GLCM window size, which is a parameter that is used in the gray level of co-occurrence matrix operator. Then we have pixel spacing, which is the final product pixel size. So remember, the input product pixel size is 40 by 40 meters. It's not the resolution, just the pixel size. And the final product pixel size here we decrease to 100 by 100 meters. And then we have also the projection. So this is the final projection to which also the ice charts have been pre-projected. Here it is set to auto, but actually the auto will default to the BGS84 UTM 26 North, which will be used in the terrain correction operator, as well as the last parameter, which is the digital elevation model, again used in the terrain correction operator. Now, I will return to all of these parameters once we get to the preprocessing, where we will then go to Snap, and I will explain to you how to create the graph file and where these parameters fit into the processing. So these are the user input data that we have to set. So let's run the user input data cell, and there we go. It gives no output, and we can move on to the load and visualize input data. Now in this step, we will create a database of all input products, which will be including the product name, date of acquisition, product type, and the preprocessing status. And each product will also be visualized using a quick look image that is already present in the Sentinel-1 product. So we will just extract it and visualize it. Now let's go through each step of this code. And we start with creating a list of downloaded zipped Sentinel-1 products that are available in our input directory. We simply create here a list of all the files that contain this pattern, so Sentinel-1, and end with .zip. Then we sort those paths based on the date of acquisition. So if you remember how the name of Sentinel-1 product looks, let me show you. It includes the date and time of acquisition right here. So we can actually use this to sort the records in our list by the date of acquisition. Then we create number of empty variables that will be later populated in the loop by different parameters that will be later passed into the data frame. Now, since we are visualizing data, we also want to create a figure. And here the figure, we just basically create the figure. We set a specific size. Now the figure will contain a number of subplots. So for each of our input images, we will have a single subplot. And now finally here we can get to the loop, where we will loop over all the downloaded zipped images that we have created the list of and sorted it by date of acquisition. And we can extract quite a lot of information already from the name. So we can extract the product date, acquisition date. Of course, we have done so already to sort the data, but we can also extract the mode. We can also extract the product type. So the mode would be extra wide swath mode. The product type would be GRD. And we can also extract polarization, which in this case is going to be dual HHHV. And that corresponds basically to this code right here. So DH corresponds to dual HHHV polarization. Then we will go to read the zipped product with snappy. So this is the first time we will use the snap bindings for Python, and we will call the product IO read product, and we will read the product into memory. And here we can get also into the auxiliary or metadata of the product. So first we will use the get name, which will get us the product name. Then we will get from the product name the acquisition date, as we have done already previously. And of course, we will append the date to the list that we have created before the empty variable of date. We've done the same also for the other variables that we have extracted. And we can also convert it using the date time library into a specific date format. So instead just being 2020 10 13, we can now have an actual date. Then we also append the name, of course, and we move on to other parameters, such as, for example, the raster dimensions and the band names. Now, once we have extracted all of this information, we can close the product that we have opened in Snappy, and we can move on to check whether this product has already been preprocessed and whether a preprocessed product exists in the folder which we have designated as our preprocessing folder. So here, of course, this depends on how you save your preprocessed data, but in this code, we save the preprocessed data that it contains the first part of the name of the original product until the first acquisition date part. And then it contains a suffix of _prep.tif. And finally, if the path of prods exists, then we can say whether the file is already preprocessed or not. And again, we append either true or false into our data frame. And here, the last step in the loop is to open or access a specific file within the zipped product, which is the quick look file, which is saved in the preview folder within the product. And it's called quick-look.png. And we can simply access only this one file without unzipping the entire product. And we can visualize it using the matplotlib library. And then basically, since we have created, you remember, this big figure that is going to be constituted of many different subplots or sub-images, we have to basically here define the position of this image within this figure. So here, of course, we have the dimensions of the figure, which we have defined above as the square root of the number of our input images rounded up. And then we have a counter F for each image that we simply append at the end, which states at which position within the figure our graph or our subplot should be. And we achieve this by simply creating a counter, which originally equals 0, and then we add 1 to it at every iteration. Finally, we set the limits of the axes to 0 to 500, since the quick look has much lower resolution. And finally, we visualize it. Now, once we are finished with the loop and we have all the variables that we wish to append to the data frame extracted and put into the empty variables that we have created in the beginning, so they are here, we now have to use these variables to create the data frame. So it will contain the name, date, sensing mode, product type, polarization, height, width, available bands, and whether the product is already preprocessed or not. And finally, we will display the data frame. So let's now run this piece of code. So here we have the data frame. cannot actually see the entire data frame. Here we have whether they are preprocessed or no. Here everywhere it says yes. And of course we have the date, sensing mode, the available bands, the name, and so on. And we have this for all the products available in the input folder or in the original folder. Now, as I've mentioned before, all of my data are already preprocessed, because to preprocess a single image, it takes about an hour and a half on my machine. So of course, this would take quite a significant amount of time. So if I go all the way to the bottom, here is my visualizations. So these are the quick looks of all the images with the acquisition date appended at the top. So you can see how the ice develops during my observation period. And finally, this is my last image that I will be classifying at the end. And now we can finally move to the preprocessing of our images. In this step, we will preprocess the data using the Sentinel-1 denoise software that I have already talked to you about, and the Science Toolbox Exploitation Platform, or SNAP as you know it, and we will use it in the form of Snap GPT graph and a snappy Python package. Now, first step that we need to apply is the denoising algorithm. Now, in order to process each of our images here, we will process them in loop later on, but here we just defined a function that will apply the Sentinel-1 denoising algorithm to each of these images. Here you have some references to the authors of this software for more information. And now let's go on to have a look at this function that I defined. Now, the Sentinel-1 denoising algorithm outputs a NumPy array, which is generally very good for Python processing. However, if we wish to process the data further in Snap or using any Snap tools, this is not good for us, since all the metadata will not be present anymore. For this reason, we are using Snappy here, because Snappy can create a copy of the original product and write the NumPy array files into it. So here, let's just go through the function. The input parameters are, of course, the input zip file of the Sentinel-1 and simply just output directory where we wish to write our temporary output. Then first we use Snappy to open our Sentinel-1 product. Then we extract its width and height. So this is going to differ for each of our images. And finally, here in the first part, we create the path for the output product that we wish to write. Now, this output is going to only be temporary and is going to be rewritten in every loop. Then we create the new product to write into this path and add empty bands for the denoised data that we want to write in. So we add the HH band, the HV band, and also, in this case, we extract the incidence angle and write it as a band into our intermediate product, because we will be using it further down the line for the classification as well. So for each band, we define the name and the data type. Then we set the no data value. We set the use of no data value to true. And finally, we specify the name of the unit of the data that will be contained in this band. Now we do this for all the three bands. And we move on to copying the metadata from our original product and the geocoding as well. So we have these two commands here, copy geocoding from our original product to the denoised product, so the intermediate product. And we do the same for the metadata. Now this will enable us to get a product that we can then further process with any Snap tools. And finally, we set the writer and write the header of the file. Now we actually have to process the data that we wish to write into this file, and we will do it here. So first we have the Sentinel-S1 here. This variable will contain the loaded Sentinel-1 image, so the original zipped product, which will be loaded with the tools contained in the Sentinel-1 denoised software. Then we will move on to run the thermal noise correction for the HH polarization. Now this one uses the ISA algorithm, so the standard algorithm that is used in the Snap software, because for HH this is sufficient. Then we have the HV, for which we will run the thermal, textural, and angular correction. I will not go more into depth into how this software works. Please check these references that I have provided for you for more details. And finally, we use also this product here to extract the incidence angle, which is given as a tie point grid in the original Sentinel-1 product. So not as an actual band, but we can extract it here and write it as a band into our new product here. Basically, in this next step here, we take each of the band of the temporary product that we have created above and write our processed NumPy array. So we have them here. Finally, we close the written product. This will save these changes to the disk. And we can just simply dispose of any opened products that we had here to reclaim the memory. And at the end, we just print a message that the textural and thermal correction have been applied successfully, and the function will return the path to this temporary product. So this is the function that we will apply for the correction. We are not running it quite yet. We just load the function. So let me simply put Control-Enter to run the cell. And then we move on to the description of the next preprocessing steps. So here, as I've mentioned, we will be using a snap graph file. Now, you may ask, why are we not using snappy to process our data? Now, snappy has one quite significant problem, and that is that at least on my machine, in my version, it does not seem to release the memory that it uses, meaning that for each new product that we open in Snappy, more and more memory is getting used until eventually it runs out of memory and you can no longer continue. Now here we are trying to process 28 or 29 images, and therefore we would run out of memory very quickly since the images are very large, and in the end we are going to have 23 bands in each image. For this reason, we will be using the snap graph file, since the graph file is run in the terminal and the memory is cleaned every time a new graph file is submitted or new command is submitted. Now I have the graph described here, but let me go to Snap and let me show you how I have created it. So let me open Snap. Now remember, this graph is going to be run on the temporary file that is going to be created by the Sentinel-1 denoise function that I have above. I have one of these temporary files ready, so we can have a look how we will then use them in the graph. So let me just open the file. Here we go. And we can see that they have 3 bands. So the bands are named accordingly. So this is the corrected HH band, the corrected HV band, and the incidence angle. We can open them to examine them. And here we go. We have the bands open. So we can simply show them side by side. And here we go. So we have the incidence angle, the HH corrected band, and the HV corrected band. Now let's load the graph that I have already prepared for you. So let's go to Tools, Graph Builder. And here in the Graph Builder, you will be already familiar with it if you watch any of our other webinars. You can build step-by-step process that you wish to apply to your data. Especially useful if you wish to process multiple data sets, like in our case. And you can run the graph either in the graphical interface or in GPT, as we will do. Now, the graph, when you open it, includes the read and write operator, and then you can simply right-click, go to Add, and add any operator that you wish. Finally, you can connect the operator. So let me, for example, put the apply orbit operator. You need to connect the operators in the way you wish to process the data. So of course, you will start with read, then you will move on to any operators that you wish, and finally to write. Now, I already have the graph prepared, and I will not go into more details on how to prepare the graphs. Again, please refer to some of our previous webinars for details on that. And let me just load the graph that I have. Now I have two graph files here. This one is just one that I prepared as if it was completely newly prepared from Snap, because afterwards we will need to do some edits on it. And this one is already the edited graph file that we are using in the code. So let me use the ORIC file. There we go. Just to improve the visualization. And here we go. So these are the steps that we are applying. Now, first, you can see that for each operator that we have, we also have a tab below where we can set the parameters. Now, first, we have this read parameter. I have renamed it in the XML file to read denoised, which is basically reading our IP file, so the temporary file that we created with the corrected bands. Then it goes to apply orbit file right here. Now, we've already discussed the applied orbit file operator today in the relation to the fact that the automatic download of orbits is failing currently, for example, for my version of Snap. And we needed to download the orbits and place them into the appropriate folder. Now, again, if you don't have this problem, I will not go into it in the main part of the webinar. If you want to know how to do that, please let me know in the questions and I will answer it during the Q&A session. Now, this operator basically looks at your file and goes online to the repository to download the appropriate orbit. If your data are older than 2 or 3 weeks, usually the precise orbits will already be available. Those are the most precise type of orbit. If not, then you can try the restituted orbits. And if your data is very recent, probably no updated orbit files will be available for your product. And you can choose these do not fail if new orbit file is not found. So I don't need to choose this here. I know that for all my data, I have the orbit files available. And then we move on to the subset. Now, in this exercise, we are not subsetting the data in any big way. We are only using the subset operator to remove the border noise. So in GRD, on the borders, very often you have invalid pixels that are not defaulting to no data. However, they have invalid values that would only pollute our image. So we want to remove them. Now, you can choose the width of this border noise removal in the user-defined parameters in our code. So if I go back to the code, here at the top, in the user input data, we have this border pixels. This will simply take a 150 pixel wideband around the entire image and removes that part. So the coordinates for this are actually set here at the bottom. And we can basically set the start point, so that will be 150 and 150, and then the width and height of the resulting image. So simply here we take the full height of the image, I already edited it here, and subtract double the width that we wish to remove, so 300. Then we have here the import vector. Here we import the land polygon that we wish to use for masking the land mass in our image. And here we apply it to our data. So in the land masking operator, we use this loaded vector to mask our bands. Here, by default, usually you have two options, either mask out the land or mask out the sea. Or you can use a vector that you load, like in our case, and you can see I have loaded in the step before, and it has already appeared here. And I can also set here invert vector. So if I do not use this, then all the area that is not covered by the polygon will be removed. If I use invert vector, all the area that is covered by the polygon will be removed. So of course, that is what we want to do. And finally, we go to the GLCM operator. Now, the GLCM stands for Gray Level Co-occurrence Matrix, and it has been proposed by Haralick in 1973, and it is one of the most widely used methods to compute second-order texture measures. Now, why do we want to do this? Spatial information in the form of texture features can be very useful for image classification. Texture measures can produce new images by making use of the spatial information inherent in the image. Since we are applying a pixel-based classification, this gives us a way how to utilize an information that involves also information from the neighboring pixels and not only the specific pixel value. Now, the GLCM that is implemented in Snap offers to compute 10 different features, and we will compute all of these features for each of our bands. Now, for my Snap, there is a bug which seems to only process a single band, so I have twice added GLCM, one for computing the HH band and one for computing the texture features for HV band. The next parameter that we need to set is the window size, in which we are computing our texture features and then also the angles. So when we are talking about GLCM, it is a measure of probability of occurrence of two gray levels separated by a given distance in a given direction. So that's why we're using here the angle, and the image that we are talking about, that is the window. So in each window, this value is going to be calculated separately. I will now not go into the other parameters here. You can again check the Snap help or the original paper by Harolik from 1973 for comprehensive explanation of all of the parameters. And basically here, just note that we will have 10 bands that will be output of this first GLCM application, and then another 10 bands for the HV band that will be result of the second one. Now, these will be saved into now intermediate two different products, and we need to put them together. Now, for this reason, we are including the next operator, which is the band merge. And we basically want to merge the original bands, so the bands which are the input for the GLCM, and then also the results of the GLCM. So we will have here 23 bands output from this step in a single product. So we are basically adding all of the bands together. And finally, we have the last operator that we wish to apply here, which is the one for terrain correction. Now, you could say that since we are looking at sea surface, we do not need to actually apply terrain correction. And this is a valid point. But there are some considerations that we need to take into account. The Sentinel-1 images, especially the GRD and also the SLC, of course, are georeferenced and contain a set of tie point grids providing a link between the SAR timing and the latitude and longitude coordinates. The tie point grids are derived from a simplified Earth model, which is a flat Earth inflated with an average scene height. In addition, the GRD are also ground range projected using this simplified Earth model. Now, if we are looking at images of the coastal area, the average scene height over the ocean will not be equal to the sea level. Of course, the larger the height difference between the mountains on the coast, or if there are mountains on the coast, and the sea surface, the higher average scene height there will be. Therefore, if the image is geocoded with the built-in Earth model, what can happen is that it will result in a positional shift related to the difference between the sea and the average height recorded for this specific scene. Now, for sea ice, you could argue that this is not absolutely necessary because the resulting shift might be in order of a few hundred meters. However, for the purpose of our exercise, I have chosen to apply the terrain correction. You can also apply, of course, a ellipsoid correction, which is simply going to use this simplified Earth model with the average scene height and just ignore the positional shifts that may result out of it. And in the terrain correction, we also need to use a digital elevation model. So this is why we have set a digital elevation model name in our user input variables right here. And we have also set the pixel spacing here. So this is also for terrain correction and the projection. So if I go back here, this is where my digital elevation model is set. Then I have here my pixel spacing. And here I need to set the map projection. So that will be here, the automatic. And you can see that it defaults to UTM zone 26 based on the VGS 84. So this is the last step in our graph. And finally, we of course have to write our image. So we will choose the directory as the processing directory, and we can put whatever name here of our final image and save it as geotiff. Now, of course, this is as you would build the graph in the graphical interface, but this is not ideal because now all of these variables are hard-coded in this graph. So if I now close this graph and go to the folder where I have loaded it from, so to my aux data folder, and I can open it with Firefox, for example, and you can see that like this, the graph looks way less readable than in the graphical interface, of course. But if you know how to read it, it actually is quite simple. You have nodes for each of the operators that you're applying. So for example, here we have a node for the apply orbit files, and you can also see all the parameters. You can see that the source product for this operator is the read denoised, so the previous node, which reads the denoised data. And we have also here the specific orbit type. So in this case, the Sentinel precise that will be auto-downloaded. And we can go down and see each of our other operators. Here, for example, we have the subset. Again, we have the source product set to the result of the apply orbit file. And we have the region, which now contains our changed parameters here to specify the exact subset that we want to create to remove the border noise. And we can just continue down to the terrain correction. You can see that automatically it gets here the projection definition. We have the pixel spacing value here that we chose, and we also have the name of the digital elevation model. Now, you can see that all of these parameters here are basically hard-coded for our specific image that we have chosen. And all of them would be saved with the same name. Now, that's not ideal, and we cannot change it on the fly. So what we can do is we can edit this file to change some of these that are hard-coded variables to actual variables that can be changed within the code. Now, let me open also the second graph, so the one that has already been edited. And here in the edited graph, you can now see that instead of having the full path as we have here in the original file, we now have this $sign and a name of a variable. So we can choose whatever name of the variable we want, and the $sign signifies that the code should be looking for a variable to enter here that is supplied from the outside. So I will get back to that a little bit later, but basically we have done this with many other variables. So the input file path, for example, the border removal, and also, for example, the window size here. You remember we have set all of these in our code. So if I go back into the user input data, you can see we have the GLCM window size. That will be the variable that is then input here, window size. So once we have edited the graph like this, we can do the edits, of course, not here in Firefox, but if we open the file in a text editor such as Mousepad, for example, that I have here available, but any text editor will do, you can simply just edit any of the names, for example, here, and save your edit, and basically then you have your graph ready to be run. You do need to pay attention to which parameters you change to variables, and you need to feed all of your variables into the code later, because otherwise you will receive an error if you do not. So let me just close this graph now. I will not save it. We will also not need these graphs anymore, and let's go back to the code. So I have been here in this place here, and now we have the graph prepared. We have it edited. It looks like this. We apply all of these steps, and now we can move on to actually applying the graph in our code. So here first, we want to create a list of the data that are already pre-processed. Now, as you know, my data are already pre-processed, so I will not actually run any processing here because it's very time demanding. And if any image needs to be pre-processed, it will be added here. If it already is pre-processed, the path will also be added here. So in the end, we will have a list of all images pre-processed. Now, we loop again through all the rows of the data frame that we have created above. And in the first step, we recreate the path to the original product. So you remember the data frame does not include path, it only includes name. So we recreate it here, but we know the input directory, so the original directory, and we know the name of our product. Then we go to the column in the data frame, which is called preprocessed. And for our product here, we check whether this column states true or false. If it has been preprocessed, we print the product has already been preprocessed in green, and we append the path to this preprocessed product to the prep data list. If the preprocessed column for our product states false, then we print we are preprocessing the product and we start the preprocessing steps. Now I have here the start date and end date. That just means that we are measuring the time that it takes us to preprocess this product, and in the end we print it. Then in the first step, we run the function that we have defined above. So that's going to be this Sentinel-1 denoising function, or do Sentinel-1 denoising. So we run it here and we supply it with the path that we have recreated here to our original Sentinel-1 product and with the directory where we wish to save the temporary product. Then once this is done and the temporary product is created, we move on to the next step, which is to preprocess the data with the graph. Now the graph cannot be processed directly in Python, and we have to process it in GPT in the terminal. Python luckily has a useful function to call the terminal and pass commands to it, which is called subprocess. And if you remember, we have defined a function above that will do this for us, and it's called execute. Now in our graph, we have these parameters that we have converted to variables that we now need to assign. For example, we need to assign the border removal parameter. The border removal parameter is actually a string that consists of 4 numbers. And these, of course, are here the start X pixel and start Y pixel, so in the horizontal and vertical direction. So for us, is going to be set to the border pixel number that we chose above. And then we check the image height and image width, and we subtract double of the border pixel band that we chose to remove from each of these numbers to find the final output width and height in pixels. So we get this string of the 4 numbers, and we continue to the next parameter, which is the output path. So basically here we just create a new path that consists of the directory where we wish to save our preprocessed product, the base name of the original product, which is split, and we only take the first part with 0, and we add a suffix. And then we move on to the creation of the command that we wish to pass to the terminal. Now, when you call snap from the terminal, you simply type GPT, and if it's correctly installed, you will see that it works, and you can pass to the GPT either a graph file with hard-coded parameters as we have, or you can even run a single operators in GPT. So I have the graph file here, and I have the path that I have defined above to my graph file, and then I have the variables. So since the code is going to be looking for variables because I have marked them with this $sign, my first variable is called input s1 denoise, and I will pass the path to my input denoised product, so the output of the denoising here, which is a path to the temporary product. And you can see that I'm using this little function that adds the quotation marks, and this is just for the purpose of not creating problems if there would be spaces in my path. Then I have the border removal parameter, again as defined in the graph file, and I pass it the parameter that I have created here. Then we have the mask vector, which in this case is the path to the mask file, so to the landmask file. Then we have the window size, again defined above in the user-defined parameters. And then we have the DEM, the pixel size, and the final coordinate reference system that we again have defined above. And we pass them with the name of the variable as defined in the graph. And here we finally, in the write operator, we had this output path So we have the output path to our output preprocessed product. Now we have these parts as a list, so all of these strings as a list, and then we basically just use the join here to connect all of these different parts in the list with a space, so there will be space between them, and pass this connected or joined statement to the sup process to execute this command in the terminal. This is much more time efficient than using Snappy for the simple reason that after every run, the terminal closes down and reopens again for the new product that we wish to process. So in the new iteration of this code, it will be opened again, and it will by that release all the memory that it is using. And when we are done with the preprocessing, we change the preprocessed in our original data frame to true. And we will also append the path of the preprocessed product into our prep data list here. Now, this is maybe not absolutely necessary to change here, but just to keep the record. And finally, we check the time and we print the time that it took to process the product here. Now, if I run this step now, you will see that for all of my products, since they are all pre-processed already, it will just print that they are all pre-processed and all ready. So let me do this. And here we go. And we can move on to the next step. In the next step, we just visualize a single pre-processed product just for your information to see all the bands that we will be using. So let me just again go through the code. We call the single product, which was going to be the last product that was processed, so the last product in our time series, and we, in this case, open it with Snappy, and we create a list of band names. Now, for example, Jadal does not allow us to extract the band names, so Snappy in this is very useful. And if we want to have just a header for each of our images that specifies the band name, we can do this like this. However, opening each of the bands using Snappy and loading it into a NumPy array for visualization would take a long time in Snappy, so we just used Jadal because it's much more efficient in this case. So here we open the image again with Jadal, and we create a figure. Again, the figure will consist of multiple subplots. We don't know at this point, we don't remember, let's say, how many subplots we need to make. So that's why we again create a final square figure, which will have the dimensions of square root of the number of bands, which is rounded up. And then we loop through each of the bands and we visualize a small portion of it, again, just to save time. So we will visualize only 2000 by 2000 pixels here. So let me just run this little code. And here we are. So we have 23 images, as I mentioned before. And you can see the texture features. Some of them look very similar, but actually the values are not all that similar. And we can investigate how they look, basically. So this is our input data for the extraction of the training data and of course for the classification as well. Actually, this last image is the one that we will use to classify, but we will not use it to train the model. We will use all the other 28 images to train the model. And first, before we get to the training of the model, we have to extract the training and validation data. Now, remember, I've mentioned that I have created this shapefile with 1000 randomly placed points in my study area. And this is where I convert this shapefile into a list of coordinates, X and Y coordinates in the UTM-26 projection. So here I just take the sampling points, load them using the GeoPandas, and extract the 3 attributes. So the attributes in this shapefile are the geometry and then the UTM zone 26 easting and northing, so the coordinates in UTM-26 north. Then I just index them, and finally I create a list of X and Y coordinates. So let me simply run it. There we go. And now I'm getting into the point that I need to look at my ice charts. Now we have downloaded the ice charts, we have reprojected them, and now we want to match them to specific images and extract the training data from them. I have, for the simplicity of the training, limited the number of classes that we will be using. So in the original ICE chart that you see in the subset here, we have these 3 classes for the first year ICE. In my classification, I have resampled this ICE chart and I have changed these 3 classes to a single class. So to do this resampling and to simplify also the ICE chart in other ways, we first need to create a list of our charts. So we do this here. You know that the charts have this pattern in their name. So they end with shapefile and they have in their name the word Arctic. So I can use it to recognize the chart files and I can create a list of the path. Then I create an empty dictionary that I will populate in the next step. And that is here. So for each of the charts that I have in the list of the paths, I want to extract the date of publication, which again is contained in the name of the file. So it's very easy to extract. And then I convert it into a timestamp using a datetime package. This is just for the purpose that when we are calculating the difference in days, it's much easier to do it with a timestamp than it is with a string or something like this. So that's why we convert it into a timestamp. And then finally, we populate this empty dictionary that we have created. And basically, we use the timestamp as a key. And then the values for each key will be the chart path and the chart date as a string. We will be using this dictionary later to match the charts and the images. In the next step, we also have to reclassify, as I've mentioned above here, the chart to basically aggregate some of the values. In the shapefile, you can actually find multiple different values. So that's why we are changing the coded ICE values here to values just from 0 to 4 for the different categories. So we have 0, which is free ice and corresponds to these 2 categories. Since we cannot really, in our pixel-based classification, recognize icebergs, that's why we are including this glacial ice class as ice-free. That is not ideal, but for iceberg detection, you do need to apply a different methodology, so that we will not discuss today. And then in class 1, we will aggregate the new ice classes, so the ones that are seen here as pink. And in class 2, we will aggregate the young ice classes again. And now these codes correspond to the codes as defined by Sigrid, and they can all occur in the ice chart as shapefiles, so that's why we are putting them here. Now, number 3 is the first year ice. So again, we are aggregating all of these ice codes under the label 3. And finally, we have the old ice, which we assign to 4. Now, number 5, class 5, later will be assigned as no data. And again, you can see that this is a dictionary, and for each we have the key, which is the new class value. Then we have a list of parameters for each key, which is the list of corresponding classes in the original ice chart and the name of the category. So once we run this, we are ready now for the extraction of the training data. And in this step, for each preprocessed image, we find a matching chart, and then we use the sampling point coordinates we loaded in the one step previous to extract the stage of development and the value for each band of each image. In total, 24 values will be extracted for each point, so the 23 bands and the stage of development. So this process takes a very long time because you can imagine we have 1,000 points for each band. Now, if we go through the single steps, I have here another data frame that at the moment is empty, and it's the training validation data frame that I named. And then we loop through all the preprocessed images with the exception of the last image, which we will later use for the final classification. And then we open the image, we extract the acquisition date of the image and convert it to timestamp. And then we use the acquisition date timestamp and the chart publication date timestamp to find the offset and to find the chart that has been published no longer than 4 days after the acquisition date, but also no earlier than 1 day before the acquisition date. Then we calculate the date offset between the image acquisition date and the closest ice chart. And then we check if the offset is larger than 4 days. Now, if it is larger than 4, then we continue to a next image. And if it's smaller than 4, we continue with the extraction of the data. First, we open the chart, or we get the chart path. Then we rasterize the chart using the function that we defined above for this, with the attribute that we wish to rasterize is the stage of development. Then we apply the sampling points. Then we convert the sampling points to an array of the same size of the preprocessed data that we are looking at. And finally, we create a zero-filled multidimensional array to which we load all the bands of our preprocessed image. And for each of those, we extract only the points corresponding to the sampling points. And then we create a temporary small data frame to which we append all the values, which are, for example, the image dates, the chart dates, the difference between dates, and the stage of development value, and the values of all the raster bands. And finally, once we are done with this small data frame, we append this data frame to the main training and validation data frame. Once we have done this for all the images and our training and validation data frame is populated, we now have to clean the data a bit. Because remember, it can happen that some of our points are falling into no data value, and we cannot have that in our training data. So here we first check if there's no data value in our stage of development, because those have different value than the band values. And basically, we just remove any rows that contain no data value in the stage of development column. Then we check again the other bands and drop any rows that contain no data value in any of the band values. Finally, when we have cleaned the dataset, we have to resample or reclassify the stage of development values that we have extracted based on the little dictionary that we have created above. So now let me run this step. And here we have our result. So you can see that below my code, now I have a table. I only show the first 10 rows of my data frame. And we can see also all the values. So we have the image date, ice chart date, date offset, stage of development from the ice chart, which is reclassified into the code that we like, and then values for all the bands within the product. Now, here we only see the first 10 rows. If we want to know how big our product actually is, or how big our training dataset actually is, we can simply just add a row here, and then I will type tv_dataset.shape. And if I run this cell, you can now see that the shape of the entire training and validation dataset is 20,417 rows. So of course, some rows have been removed due to the fact that they contained no data or invalid data. And we have 27 different columns. Now, in the next step, we will use the sklearn library to split our dataset into the training and the test dataset. So first we have our Y data, which is of course going to be the truth values, and then we have the features we wish to use for the classification or for the training of the model. So here to the Y, we assign, of course, all the values of the stage of development. And for the X, we choose all the values in all the bands. So this will correspond to all the band values here. We just put value bands here, but this is because this value corresponds to a list of the names of the bands, which are also used here as the column names. And then in the next step, we split the data set. So we will in the end have 4 different data sets that will be X-train and X-test, and Y-train and Y-test. Now there is this little functionality that allows us to do it with one line, and we just feed it simply the Y and X data here, and then we choose the size of the resulting testing data set, and we wish to use here only 20% of our data for testing. And finally, once we have run this step, so let me run it, we arrive to the classification or training of our model of our random forest classifier. Now, random forest is a machine learning technique that can be used for classification or regression. Now, unlike many other classifiers, the random forest does not start with the data model, but instead learns the relationship between the training and the response data set from the training data set. Now let's explain a bit how random forest works. For each tree, a different subset will be drawn from our training set. The subsets can overlap and can contain the same samples, and then a specific number, for example, for our model, we will be using 500 trees. Specific number of trees is created, and each of the trees is trying to split its own subset to the most clean split between the classes based on the features, or bands in this case, that we supply to it. Now, we will use the random forest implementation provided by the scikit-learn library. It's one of the most used library for any machine learning applications. And let's now continue to train our classifier. Now, I have pre-run these cells for the simple reason that the final prediction of our image takes quite a long time, between 10 to 15 minutes. And of course, again, we don't have time for it in this tutorial. So you can see that I have already run my cell here, and here I have an output. And just to go through the different steps in the cell. So first, we will initialize our model, and we chose 500 trees, which is a value that is quite commonly used. Then the next step is to fit our model into our X and Y training data. Once we do that, these mathematical relationships between the X and Y data using all the features are created, and our model is trained. Now, we can also choose here already in the beginning, when we are initializing our model, that we wish to output a score, which is the out-of-bag estimate, meaning that it takes part of our training data and creates an estimate of how correctly this data is classified. Now, here we see the result of this. So the accuracy of our model on our training data is 70.99%, so 71% approximately. Now, this is not a great accuracy, especially not on the training data set. However, as I've mentioned before, we are not using a lot of images. If we use more images, if we use different incidence angles, for example, then this should definitely be increased. And then we also have the feature importance scores. So feature, in this case, we mean, of course, the bands that we feed into the classification. And for each band, we have an importance score. Now, they're not sorted by the score, and I will not go through them. But if you wanted to, for example, simplify your classification for future things or find out which bands are the most important for your classification, you can use this score to determine which bands you can, for example, discard, and by that simplify your processing. So once we have our model trained, we can also output a model statistics based on the test data set, X test and Y test. We did not use to train the model. And now we can basically use our model to predict the values of Y, or the stage of development values, based on the X test data set, and we will receive the Y predictions. And then we can compare the Y predictions and the Y test, which are the true values extracted from the ice charts, and see the statistics of the results for our 5 classes. And the resulting table contains values per class for precision, recall, and F1 score. Since we are running out of time, we will only look at the F1 score, which is the weighted harmonic mean of precision and recall, such that the best score is 1 and the worst is 0. So for us, the ice-free class has the highest F1 score, followed by the young ice and first-year ice, and then by finally old ice has the worst F1 score that we can have, meaning that the results are not very good indeed. Again, as I've mentioned, we are not trying here to get the best results possible. We can make many improvements to this code. For example, for new ice, we have very, very little samples in our data set. That means that it cannot be correctly classified. Now, when we see the model statistics, we can go back and try to change our training data or increase the amount of the training data that we have to improve our result. But if we like the result, we can continue to use this model for predicting an actual data set that has not been included in the training data to begin with. So let's say we want to use this data set to predict the stage of development on an image for which we do not have any ice chart. So that would be the next step to classify the last image in our time series. Now, of course, we have an ice chart corresponding to this image, but if we wanted to use this model to classify all the future images and not to have to make any ice charts, this is how we would do it. Now, I have already run the classification, as you can see, and we have classified the last pre-processed image in our series. And just to go through steps again, first we have created an empty multidimensional array, same way as we have done when we were extracting the training data. Then we reshaped this array into a long 2D array for classification. And finally, we change all the no data value to an actual value because we cannot classify with NaN values. So we change the value to -9999. You can choose whatever no data value you wish, as long as this value is not represented in your valid data. And then we move on to predict each of the pixels based on our model. And finally, we reshape the final class prediction again back to the size of our array. And we can continue now to the post-classification filtering. Now, here in this tutorial, I am using pixel-based classification. And that will generally result in quite noisy result, especially when using SAR data. And we can try to smooth the result by applying, for example, majority filter, which is run in a moving window of defined size. And in each window, the mode, so the value that occurs most often within that window, is assigned to the central pixel. And basically, this is what this little piece of code does here. So let me run. And here we go. And we can finally come to the visualization of the result, which is the last step in our processing. So first, we define our color palette with specific colors assigned to each class. So we have blue for ice-free here. So the corresponding value, of course, in the results is 0. And then we have assigned the RGB composition of this color. Then we have pink for new ice, purple for young ice, green for first year ice, and sienna for old ice. This is the same visualization as in the little subset of the ice chart that I have shown you above. And white is assigned as no data. And finally, this is just other steps that we need to create the color map or CMap that we then pass into our Matplotlib visualization. So let me just simply run this step. There we go. And we can now proceed to the actual visualization. So here we simply just take the test image that we have already loaded when we were trying to predict the stage of development. And we load the HH and HV bands just because I thought it would be nice to have them visualized all next to one another. And then we calculate, just for the visualization, the values of 5% and 95% percentile to enhance the visualization of the histogram. And then we move on to getting the corresponding ice chart. Again, here I provide it specifically by name. And I extract again the stage of development values and apply a mask, the same mask as is defined above for the classified values, just so we have the same exact visualization. And as last, we move on to creating the figure, which in this case is going to have 4 subplots. So 2 subplots for the HH and HV polarization, 1 subplot for the true values of the ice chart, and finally our predicted stage of development, so the classification. And finally, I create a color bar below, which is going to be horizontally oriented. And I set also the tick labels for each of the values. So instead of values from 0 to 5, we will now have the name of the classes. And let me run it so you can see the final result of this entire exercise. And here we go. So here we have the HH polarization and HV polarization. And here we have our stage of development ice chart and our stage of development classification. So you can see they actually look relatively close to each other. Here we have a color bar with all the different classes and colors. And we can see that for example, our first year ice is relatively well classified, as well as the young ice. But the old ice, we have a bit of an issue here. There's not so much of it classified in our result. But again, maybe increasing the number of training data samples or so on can increase our accuracy in that matter. So actually the image that we have classified has been from the 22nd of March, whereas the stage of development ice chart is from the 26th of March. So it's 4 days. The image has been acquired 4 days before the publication of the ice chart. And we can see that actually they seem to correspond to each other very well. So probably around 4 days before the ice chart is a good bet that that is going to be some of the images that are actually used to derive this ice chart. So this is all for me. I hope you have enjoyed this extremely long webinar, and I will not go on about how to export the data and so on. There is a lot of information online, and if you're interested, I can also tell you during the Q&A session. I hope it was interesting and inspiring for you, and I will now go back to my presentation and to the Q&A so I can start responding to your questions.